Hello, everyone. Good afternoon, good morning, good evening, wherever you are. And welcome back to the second segment of multi-level linear models, also called hierarchical linear models. In the first segment or the first section, we talked about clustered data. So we said that clustered data are usually collected by design. Sometimes you have all the teeth in your mouth and doctors work on them. And when they collect all that data up from the different patients they've worked with, they have individual teeth, but those teeth belong to different people. So there's clustered of the data. But let's move forward and start talking about how we address or what happens when we're addressing a hierarchical linear model using what we call random intercepts. So I'm going to take us through very quickly, and you can watch this at your pace and watch it again, but I'll try to take us very quickly through what random intercepts are and how they help us address the issue of clustering in our analysis. Okay, so remember from our linear regression, you have an outcome which we'll call your dependent variable, your response variable, and then you have your beta naught, and this beta naught is called your intercept, and you have your beta 1 or your x1, which is your individual level predictors that you're trying to look at how they affect your outcome, and on, bx, b beta 2x, and so on. Okay, so as part of the refresher, let's look very quickly. You're looking at the study. You want to understand whether women have a higher BMI on average than men. You have your dependent variable to be BMI, and of course you have your intercept, and you have if a person in your study is female or not as your beta 1. And so the question here is, as a refresher, what is beta 0? What is beta naught? Oh, did I hear you say that beta naught is the average BMI of the people in your sample? Whether they are male or female. Well, if you said that as your answer, the answer is not correct. Your beta 0, because this is beta 1 for female, your beta 0 is the average BMI of everybody who is not female. And so you have this average BMI for everybody who's not female, which is average BMI for men. And then if you are female, you get this additional beta to your BMI. And this additional beta may be negative. It's just maybe how do they say that? A trick question there, but to make you remember your regressions. Okay, let's move to the next. So we have a more complex example with more individual level predictors and also with an interaction term. And so you're looking at your BMI, but now there's whether you're male or female, whether you go to school, what type of school you go to, not whether you go to school, and whether the particular school you go to affects or influences or interacts with whether you're female to give you an effect. So here, what is your B naught? Your B naught is just like we did in the previous example. Your B naught is the average BMI when your predictor variables are 0. So in this case, if you're coding sex female as 1 and sex male as 0, this B naught and maybe a school where they do exercises versus schools where they don't do exercises, schools where they do exercises 1 and schools where they don't do exercise 0. And so your B naught would be the BMI for a person on average who is not female, that is, who is considered male sex-wise, and who goes to a school where they do not do exercise. And of course, the interaction term would be they do not do exercises in their school and they're also not female or they're male. So this sets the stage as we go to talk about your random intercepts. Okay, multi-level models. What happens is we're now putting a twist on your interaction term, but also there's more information that is coming out of this relationship that we saw earlier. So we're going to look at what is our B naught. So our B naught is, just as we said, it's your outcome, it's your average outcome when every other thing in the model is 0. But what is your B0I? These are a little tricky. So what is your B0I? Your B0I is the value with which your global average, this your B naught, would change for each level of your hierarchy, of your grouping. And of course, your EIJ is your is your error term. Okay, we're going to go more into it and look at an example, and then this would start to make sense for all of us. All right, so let us do a quick example before we go into this, for example. So we were talking about at the beginning of this section, if you were a patient with cavities in your teeth and you were in a study and the dentist worked on multiple teeth in your mouth and did that for several other patients, you are considered to be a cluster, a hierarchy, a group. Another patient with multiple teeth in their mouth being worked on are also a group, a hierarchy, a patient. And so let's say what they're looking at is the number of caries on average in patients, you know. So let us say that um, let us say that your B naught would be that general across everybody in the study. What was the average number of caries, you know, or holes in your teeth? This level here, this B01, we're saying that how does this average number vary from individual to individual? And what happens with your hierarchical level modeling is that you are assigned an extra. Remember when we were talking about females, we said it can be negative, it can be positive, but each individual is assigned an extra coefficient, such that if you were looking at me, the global average might be 2 caries in my mouth, but because I am me, I am an individual, I am a group, assigned to me maybe 0.5, assigned to another patient to be 3, and but as they would also have the average of 3, but assigned to them would be maybe 0.2 or 0.1 and so on. And so what you have in a multi-level model is that you can understand how each individual person, not individual person, how each individual cluster, in this case of the dental research, each patient varies in terms of the caries in their mouth. So you can see that each cluster is unique at the end of the day, instead of us to conclude that each cluster, each group, each level has the same average. I hope this makes sense to you. We're going to move into more examples as we go by. Okay, but let's with that example, let's explain it further using our formula. So in this case, we're just looking at the high level. We're not going to introduce multiple covariates as you saw with the earlier example that we had. Okay, so we're going to say that, let's look at the B naught. So B naught is the intercept we would have gotten if this was a linear regression. So if we did not account for clustering, this is called the fixed effect intercept. So you're going to be hearing things like fixed effect, random effects, and so let's get used to this. And this is the global mean. So across every observation in that sample in the population, this is the average we get. That is your B naught. Okay, but however, we've said that people or observations can be grouped in clusters. And so you need to know, how does this cluster different from the other cluster, from the other cluster, from the other cluster? And this is where you have your B0I. It is the value with which the intercept for each group differs from that fixed effect. So you cannot say that the value that I have, suppose I was a patient in this dental example, that my value is the same as this value here. No, you have to account for the fact that the teeth in my mouth belong to me and the teeth in someone else's mouth belongs to them. I hope this is going to turn out to be a good example. But it's also called the offset. So I gave you the example and now I'm merging the definitions to the example. And so what we have here is that beta 0 plus B0I represents each individual's trajectory. So we see that each individual is different. We cannot assume that the global average applies to all of them. Okay, so we don't have, in this very simple model called the null model, we've not even started talking about individualized predictors. This is just to set you straight on what we're talking about and what cluster or hierarchical linear models are used to determine. Okay, so let's move on. I know I said we're going to be very quick, but sometimes these things are a little tricky to explain. And so I hope you're following along. Okay, so let's look at an actual example. So in this study, you're looking at resident doctors across hospitals, and you want to look at whether their income is associated with the type of hospital that they are in. So these are doctors, they are individual observations in your study. But these individual observations, which are doctors, can either work in a tertiary hospital or can work in, let's call it a community hospital. So of course, our Y here is our outcome variable, that is the income. And then our beta, our Y here is of course is your income. But your beta naught here, because this is a null model, your beta naught is what is the global mean of the doctors, irrespective of whether they're not irrespective, I beg your pardon. This is the global mean of doctors on average, right? And I'm going to address what I just said. So this is the global mean on average. But now we're saying some of these doctors work in a tertiary hospital and some of them do not. And so what we have here, if you remember what we just did, we're saying if you code your working in a tertiary hospital as 1 versus community hospital as 0, we're saying that because you belong to a group where you work in a tertiary hospital, there would be an addition. And remember that this addition could be negative. It does not always have to be a positive addition. So at the group level, that group effect you're going to have, and it's going to differentiate you at the group level from people in another group. And so, okay, let's also and let us look at an R model to talk about and try to identify. So we have some data and we're looking at patients, not patients, I beg your pardon. We're looking at resident doctors and their income. So let's find together, and the clue is that these things are circled, what B naught and maybe what beta naught, sorry, and B naught I could be. So remember, we said that your B naught is your global mean, it's your intercept. And so this is the giveaway here. So we imagine that doctors on average, let's call this dollars, earn $206,517 per year in the place where you're studying. And then, of course, the standard deviation for this, the variation on average is your 3.7, but raised to the power minus 4. So it's, I'm sure that you know what to do. Okay, well, let's move forward here. So, and then we have further R extracts. Remember, we said that if you were a resident doctor working in a tertiary hospital, there would be an addition, and this addition does not have to be positive. So you're coded 1 or you're coded 0. So let's look at the R extract here. So this is negative 5.3, but raised to the power minus 11. And look at that number here. This is what it looks like in real life. So if you worked in if you were a resident working in a tertiary hospital, you would earn just a very fraction of a dollar, a very small fraction of a dollar less. So there's really no difference, at least economically, between if you do not work in a tertiary hospital or if you work in a tertiary hospital. Okay, so that's where we are. Let's do another example really quickly, and then you're beginning to see what this means when we're talking about a random intercept. So a random intercept versus your fixed, a random effect versus your fixed intercept. So we're talking about here about 400,000 children from a nationally representative survey. So it represents all the children in whatever country across Africa. Wow. And you're looking at the mean hemoglobin by country using this multi-level method. So we're back here. It's a very simple model. It's a null model. There are no individual additional individual level covariates. And so let's try to identify what our beta naught is and what our B01. So I believe we can look. I'm just going to cheat. And then there we have it. We have your fixed effect here, your fixed global mean for children in Africa. On average, your mean is 10.3. But these 400 children belong to different groups, and these groups are countries in Africa. And so we're going to see subsequently what the addition for each country or subtraction, remember, it does not always have to be an addition, looks like. So here we have the R output. And so if you were from the DR, for example, Congo DR, you would have your global mean plus your what do you call it, the random effect. So now you can see how in each cluster of a country, the hemoglobin of children vary. So the example we have here is Angola. I know I always try to move off script. I don't know why I do that, but I think it makes it more interesting. So you have your global mean of 10.03, which we saw in the previous slide right here, plus the cluster amount accorded to Angola, and that is 0.22. So when you have cluster data, the point we're trying to make here is you cannot use the global mean that you would get if you ran a linear regression. You have to make sure that your audience or whoever you, not just your audience, you understand that there are variations between clusters, and you have to account for that in your model. Okay, so let's now add a covariate. So we've talked about a null model, but now we have to talk about your when you're adding a covariate. So we have, of course, your group, not your global mean plus your group mean the additions, but now you now have an individual level predictor and you have your error term. So let's look at what that looks like in when you are adjusting or when you're running your model. Okay, so let's jump right to an example. So you are again studying the income of resident doctors across hospitals. So you're a busybody. You want to know what doctors make. And some of them work in a tertiary hospital, whereas some of them work in a community hospital. But you also want to know, do older resident doctors make more money than younger resident doctors? You know, you want to know how age this relationship. So here we are, we have your global mean, and your global mean is in this case, it's the average that doctors would earn, irrespective of whether they work in a community hospital or in a uh, tertiary hospital, right? But now we're saying that if you coded your tertiary hospital as 1 and your community hospital as 0, of course, your global mean would be your average of people who do not work in a tertiary hospital. And your B0I here would be the addition. Okay, so let us look at how age affects this model. So let us look for our intercept, our fixed effects. Oh, I cannot see it. There's no circle. Okay, let's do it by ourselves then. So when you put in the age as a continuous variable, what you have is that doctors on average, or doctors on average earn 192,000 or 193,000. But if you work in a tertiary hospital, you're going to have this addition. So doctors who do not work in tertiary hospital earn about 193. And if you work in a tertiary hospital, we saw that it was very small. But also, if you depend for every unit increase in age, I'm guessing from 0, from 0 to 1 to 2 and so on, you would earn an additional $389 as a doctor, So this is an individual level. It's not a group level, as a doctor. And so in this model, we've said, well, there are no 0 years old doctors in the world, at least not yet. So let us say that these doctors, what we're going to do is we're going to say, for every year older than 25, what is the additional amount that the doctors earn? So it turns out to be the same thing. I will not go into that very quickly. The numbers are it's kind of the same whether you subtract 25 or you leave it as is. But what you can see is that the intercept changed from 193. So there's adjustments for what you did by centering. I believe that is you're not centering the mean, but everybody on 25, how much older they are than 25. We're scaling the continuous variable. So this increases, this stays the same. And then what we have is our variance and standard deviations is 0. That's interesting. And so the same conclusion is reached. So if you were a doctor let's imagine that change between if you were not in a tertiary hospital, if you were in a tertiary hospital, you would have that 0.05 times 10 raised to minus 11 added to your pay. But for every year above 25, your pay will increase by about $400. Okay, so let's jump into the hypothesis testing aspect. We've not talked about p-values. We've been talking about your your models and how to understand the structure of the model. And something to note is that when you're doing your basic hierarchical models, when you're using certain methods, or when you're using the generalized, not, no, when you're using, when you're doing your hierarchical modeling, you most often will not get a p-value for your predictors. But what you would need to do is you would need to compare the two models. So you compare your null model versus the model that you have your individual predictor. And the p-value you get would help you determine whether you should whether you should go with the fuller model, that's the one with the individual predictor, individualized predictor, or you should go with your smaller model. And that gives you a sense of whether that added individualized predictor is statistically significant. And so if your p value is greater or equal to 0.05, if it's greater, you have to take the lower model or the smaller model. If it's lesser, you want to, excuse me, you want to go for the more complex model. And this is called the likelihood ratio test. So let's look at our example. So we compare in R, we compared the first model, which looked at, not the first model, the bigger model, which looked at your individualized um, predictor added. That's the age 25 versus the null model. And what we have is your p-value spat out here as 0.07. So we said if your p-value is bigger than 0.05, you want to go for the parsimonious model because there's no difference between both of them. So just go with the simpler model. So you can assume, or you can conclude, that the age is not exactly relevant to your modeling. Okay. So this is the same example. Now we've broken down whether the age, remember that we started with zero, age on a scale of 0 to whatever, then age greater than, for every year greater than 25. And we're repeating this model with your age, are you greater than 40 or not? But we're not going to go through this when we teach the class, or you can go through this yourself and try to look and identify where these the statistics that are created in R are, and reach your own conclusions. Okay, so we've come to the end. We've discussed the random, the fixed effects, the for a hierarchical linear model. And I hope that you've either understood it, and if you've not, you can always go back and look through and read through, and maybe ask questions when we meet in person. As we come to the end, think about studies that you're currently planning. What would be the grouping variables, if there would be any, and what would be the individual level variables that you would consider in your model? So thank you very much. I hope this was useful for you, and I hope you understood the presentation.